All right, cool. Okay. Thanks everyone for coming. Today I'm going to give you a bit of an update on what I do and the work I've been doing, the recent work I've been doing the past year and a half. So I hope the title sort of summarizes what I do. So antennas for landmine detection using ground penetrating radar, with a main focus on antenna design. But also doing some radar measurements to verify the antenna concept. So this is pretty much the layout of the presentation. So I'm going to give you some introduction. You've probably seen the introduction before, so I'm going to repeat why I'm doing what I'm doing. Just bear with me if you've seen this before. Then I'm going to sort of go through GPR principles and how you can use 3D modeling to characterize the whole problem. And then I'm going to introduce very briefly the antenna design and the measurements and verification. And then the radar measurements that were performed using the antenna and their conclusion. So this is just, can you all see that? Mm-hmm. So this has just been published recently, so November 2015, and it shows the mine contamination around the world. And as you can see, there's still staggering amount of landmines still present. The problem is not just third world countries. As you can see, in Europe, there are still explosive remnants from past World War that are still haunting the eagle. And the numbers are just scary. You have a lot of millions still out there. Although the total number has been reduced, but there are still countries that are not part of the October Band Treaty, so they remain non-signatories. So they can use landmines, produce landmines, and they can use landmines at any time. And I believe there are some examples right now happening in possibly Syria or Libya. So yes, it's a big problem. As well as military, I think mines are also a humanitarian challenge, because there are weapons that don't distinguish between civilian and enemy, as well as animals. So they have class of damage. So these things remain underground for decades, and they can still hurt people on many levels long after the conflict have been So I'm just going through, so what are landmines? I think in general description, they are a container of explosives, shaped in a different sort of geometry for many reasons. So on the left you have, I've just selected a few anti-personnel landmines, but there are over 350 types of anti-personnel landmines out there. So you can see how they vary in shape, in mechanisms, the trigger mechanisms. On the right, you have anti-vehicle landmines. They are much bigger, contain a much more amount of explosives, but rather they are easier to detect because they are metallic and they are large, as opposed to the anti-personnel ones, because they are small and they are mostly made of plastic. That's what makes them quite challenging to detect. As well as landmines, you have other types of explosive containers, for example, ammunition shells and mortar shells, being used in different sort of, applications. So these are known as IEDs and UXOs. You can see how the anti-vehicle landmines can be used as IED and mortar shells. But yeah, in general, they get the containers of explosives buried either under the ground or on the side of the road to inflict as much of damage as it can. Minefields. So again, this is a huge topic. You can go through the literature of how these mines are buried. They can be buried manually, or they can be scattered around by moving platforms, which then when they up on landing, they could be sort of laid, not necessarily flat, but they could be inclined or an angle when they're below the surface. The other thing to notice is the material, the surrounding environment that they are found. So they could be dry sandy soil, there could be vegetation, beach sand, vegetation here, and this is showing how they could move around by the conditions of the environment. So the moisture and the movement of the soil. These things can move around, can be relocated, go deeper or come to top of the soil. So these are all sort of influence the puts a lot of challenge on the sensor, and yeah, depending what you want to. I think in my experience, if you design a GPR sensor, you need to sort of narrow down your sort of problem. You can't just design a GPR sensor that will work in all the applications. I think that's very quite challenging. So that's why most GPR systems are quite narrowed down, that they're specifically looking at possibly one particular material or one particular sort of landmine. So just a very brief sort of idea of the current technologies, or the technologies that are being developed or looked at. So here it's the most cheapest one. There's a guy with a prodder sort of trying to probe the ground, and as you can see, it's pretty dangerous because it puts the life of a person at risk. And it only works with the landmines that are shallow, so if it's deeper, you can't really detect anything. And you might accidentally trigger the landmine because you're just probing the landmine from the side or top. Here is maybe the sort of the second most used technology, metal detector. But as the name suggests, it only detects metal. So it's good for anti-vehicle landmines, but for anti-personnel landmine that it contains a metal as small as maybe a spring of a pen, it won't do any good. On the right, this is a concept that's been developed. It hasn't reached a level of maturity for it to be operational, but the idea is to use vibration of sound to make some vibration in the soil, and then pick up the resonance or vibration using the laser from a good distance. On the left, it's the most sort of unethical of doing this. So people are using dogs and rats. This is a special kind of rat only found in Africa. They can smell the landmine, so you strap it into a string and make it go up and down a lane. Same with dogs. Here in Croatia, they're using bees to sort of, I think they have an unnatural behavior when they come across landmines. And then on the left, there are genetically modified microorganisms that, when they come in contact with landmine, they change color. That's another sort of technology that they're looking at. But out of all, the most promising technology is GPR, so ground penetrating radar, that most systems are using the technique. Just a very brief concept of a GPR. So you have, so it's a radar, but it's called the ultra-wide band radar. It's a special kind of radar that sort of looks into the, instead of free space, you look into dielectric medium. So it's not a conventional radar where everything's far field. In this case, everything is pretty much near field. So it's a different technique. But the sort of sensory configurations stays the same. So you normally have a transmitter and receiver. It can be separated, biostatic, but some people don't like to call it biostatic because they're still close to each other. but still you transmit and receive from a separate antenna receivers. Or there could be one, you transmit from one antenna and receive from the same antenna. And the data is processed and displayed as a sort of as a radiogram or a 2D image where the user can sort of read or visually see the data. So that's a free space dielectric. And when the radar penetrates through the dielectric medium, you have a few factors that will affect that signal. So you have the penetration depth, which directly mainly relates to attenuation. The target size and shape also determine how much signal you get back, and the geological conditions of the material, if it's wet or dry. And also, as well as the distance of the radar to the ground, that also has an influence. So again, generally, before you design any GPR sensor, I think you need to look at two parameters: what target you are trying to detect, what size it is, what material it's made of, what environment you want to look at it. So if it's dry, wet, different material, if it's dry sand, if it's loamy soil, beach sand, and then come up with the parameters. So how much frequency, how much bandwidth you need, what operating frequency, what polarization. And then once you've sort of drawn all that specification, then you can come up with a radar to antenna design. Again, in my experience, the two main factors that decide the detectivity of a target is the integrity of the signal through the antenna and the dynamic range of the radar. So these two, I think, ultimately decides the distance of the target. So I'll just try to summarize modeling in one page, and I think it's too much in one slide, but hopefully I'm going to go through it. So on the right, so 3D modeling, as you are familiar with it, we use CST Microwave Studio, so it's a very good 3D automatic software that you can use to model and simulate your environment. So on the left is just a summary of sort of chosen how you can characterize GPR. So, for example, you can look at the soil and look at the return signal. Before you actually look at the soil, you can measure the soil, import the dielectric properties, the real dielectric properties of the soil, and then import it back to CST. So you're now looking at real data, not just simulated sort of data. And then you can, again, there are many ways of characterizing. So you can place receivers or probes inside the material to look at the signal level as it propagates. You can look at one-way attenuation through the material. And then you can look at the signal level, so you can place targets inside the plastic and then change its depth and size to see what's the sort of level of the signal that comes back. So here it's a graph of signal level for a plastic target, that varies in size. So on the x-axis you have varied depth from 0 to 10 centimeters, and on the side we have the two-way return signal. So going back, going hit the target and coming back in dB. So you can see for the smallest target, 5 centimeter by 5 centimeter, you have a very low sort of return signal. And then as the target gets bigger, the return signal essentially enlarges. So assuming that you're looking for a plastic target that is 5 centimeter by 5 centimeter, your return signal at 10 centimeters is about 125 dB. So that means your radar has to have a dynamic range of that level to be able to detect it. If anything above that, then you won't be able to see it. This is assuming that everything, the signal integrity and everything is stay the same, no losses and no path. Again, so you can look at the soil, you can characterize the soil and see what actually happens when the radar signal goes through it. So this is really a spectrum, so frequency against amplitude. And first one here is the spectrum of the dry sandy soil, So you can see the red transmitted signal and the green received signal. The received signal doesn't really change in frequency, but you can see it's a bit distorted as it goes through the dry sand. But for concrete and wet sand, two things that you can notice is, first of all, the level of the received signal is reduced, so there's a lot more attenuation, but also the high frequencies have been shifted to low frequencies, so it sort of acts as a low pass filter. That's for wet sand, that's for concrete. And over here you have again another way of looking at so this is the simulation of sending a radar signal through a material and then seeing what the signal level is from the other side. So it's one-way attenuation. So this is for dry sand and wet sand. On the x-axis you have the depth, which is varied from 0 to 30 centimeters. On the y-axis you have the one-way attenuation. You can see going from 0 to 30 centimeters for dry sand, you have a loss of about 10 dB or 12 dB. But for the same sort of scenario, different material, going from 0 to 30 centimeters for a wet sand, you have about 55 dB of loss. So yeah, so you can sort of investigate what to expect. Other thing you can do, you can introduce, so here everything is assumed as a plane wave illuminator, so everything is plane wave. And it's a really good assumption because you want to see what the parameters are. But then in a real world situation, in a real situation, you've got to have some sort of antenna. So that's something that you can do in CST. You can play around with, investigate how the antenna affects the soil. And this is just a summary of showing that on the right you have a plane wave illuminating a plastic target under the soil, so you can see the boundary. On the right you have the antenna. Now the main thing is a signal going through, so you can see it's the radiation pattern inside the soil is different, but also the return signal you get from the interface of the air and soil interface. Now, if these return signals are much higher than the return signal you get from a plastic or a target that you're trying to look at, then your detectability reduces, so you won't be able to see the target because it gets masked in. So the challenge arises by the design of the antenna. So the more it's coupled to the soil, the less of these return signals, and you get more energy penetrating through the soil and more energy coming back. As you know, amplifiers really don't work in GPRs because everything is linear. So if you're amplifying, hoping that you get more return signal back, you will also get clutter and soil relative to it. So in conclusion, to get more energy back from the return signal, you need to design an antenna carefully to couple it. But then that goes back to the scenarios. If you can design an antenna that couples to one medium, it won't necessarily match another medium. So you need to sort of have a trade-off. So that's something I've been looking at. So obviously, if you want to look at GPR and anti-personnel, anti-vehicle landmines, it's a good starting point to start with simple geometry, geometric shapes, so flat target, circle target. But then in the end, we've got to look at something that's realistic. So I spent sort of quite a while to look at, to design, to model targets to the realistic dimensions. So looking at the specification that are classified online regarding the dimensions and length and height. Sort of model a few of them, and so these are to the realistic material and dimensions. And once you've got them, then you can characterize them. So you can look at the return signal from a target in free space. You can look at the signal level that comes back from the casing of landmine, the RCS, and time domain characteristics. So this is a typical, so this is a sort of the A scan, what is known as the A scan time domain profile of a few landmines. So this is looking at, so you can see the antenna is right above the target in free space, and you get a time domain signature. So you can see it's different for different landmines, or different amplitude of return signal, and different behavior. So you can see for the longer cylindrical shapes, you tend to have more resonating because the signal will bounce within the case of the landmine, and then it comes back. And also the profile, the overall envelope of the signature is quite different for each. We can move on to B scan, so it's when you move the illuminator across one lane, either X or Y. And this is what sort of, it's typical for a landmine, and what is called a hypervela of a landmine of this type. As a comparison, you have got flat metal on the right side, and the BS50 on the left-hand side of flat and the right hand. So the left-hand side of the BS50 and the right-hand side of flat metal. So you can see for the flat metal, as you expect, it's horizontal, pretty much line, and then for a BS50 you got this hypervela with multiple returns coming back from either the void inside or the back of the landmine. And you can also look at the RCS of a landmine and see. So for example here I'm looking at RCS as a function of frequency. As you know, RCS, there are many factors that affect RCS. Here I'm looking at RCS as a function of frequency, just to investigate what frequencies are best to look at these landmines. So here on the left you got the BS50. On the x-axis is the illuminator moving in one direction, and the y-axis you got the frequency, operating frequency from 0 to 8 GHz. And so here you can clearly see the hypervela of the landmine, which is affected. But what you can notice is that for this particular frequency, the RCS is quite highlighted at two frequencies, so about 4.5 GHz and about 7.5 GHz. You get the most RCS back. So the comparison is always good to look at flat metal. So as you expect, pretty much all the frequencies is flat. In angle incident is 90 degrees, so you get most of it back. Here is a type 50 fragment landmine. Again, because it's a combination of steel and wooden material, you get most, and you can see the asymmetrical for RCS, just because it's not symmetrical. For the butterfly, this is a really nasty one because it's very, very small, very thin. So when I looked at RCS, I realized you probably need frequencies of about 5 GHz, 5 to 8 GHz to get anything back from this. You can do the same thing for anti-vehicles. The three main types that I've been looking at is D3. Again, as I said, anti-vehicles are much easier to detect because the RCS weight is quite strong across the whole frequency range, and the amplitude you get back is quite high, which is good for a radar. The next step, once you characterize the target, your step is to do a full GPR simulation and see what you get. So this is, again, so that you can design your simulation box and sort of an environment. This is the antenna that I will introduce in a bit. So you got the illuminator on top, and then you do a sort of a linear scan, recording data at every step that you desire. So I've taken data here at 15 millimeters, quite narrow spacing. So this is operating at 0.5 GHz to 5 GHz, one of the band of my antenna. And you can see the signature that comes back from an anti-vehicle landmine. You can just about see the shape of it, the geometrical shape of it, and if you assume that this is the top of the landmine and that's the bottom of the landmine, you can just about estimate the height of the landmine. This is another thing that I've been experimenting with. So as I will introduce in a bit, my antenna can function in different configuration. So inside an antenna I have another sub-antenna that operates at different polarization and different configuration. So you have, instead of just transmitting and receiving from one antenna, you have a ability to transmit and receive from different pair. So here, I've shown if you transmit from one pair, which has a slightly beam width off the mode side, it's found that the landmine, the same landmine, same scenario, the edges of the landmine is more highlighted, as you can see. But then if you switch a different configuration, you see from one pair, you transmit from one pair and you receive from the other side, the main sort of activator is more highlighted to the radar. So again, I'm just going to go through this quickly. So antenna design, the very sort of principle, first principle you look at is you've got your antenna. Before the signal skips from an antenna, it's going to hit the antenna aperture. And if you haven't designed it carefully, you get a lot of signal. The very first instant, you get a lot of signal back to the antenna. Then after that, when you lose the antenna, it's going to hit air. Air has an impedance of 377. Your signal starts from 50 ohm, so if you don't match these two, you're going to get a mismatch, so I'll return back. And then after the air, you're going to get soil. So for most soil material, the air impedance is 125 ohm. So then that has to get matched to this soil to get more coupling. And then after all that journey that the signal takes, the signal has to go through the same path to get back to the radar. So as you can imagine, the detectability of this target depends on the pathways. So this is my antenna design. So it's the overall geometry of it. Again, I won't go through the design. I'm sure you're familiar, or if you're interested, speak to me later. So it's a quite complex. Some people call it bulky, but it's more. But as a horn antenna. That has the ability to operate at different bands as well as radiation characteristics. So each band has its own radiation characteristics, beam width and time domain characteristics. So you have ability to operate from 3.5 to 7.5 gigahertz. You have the main band, which is 0.5 to 5.5 gigahertz, and you have the third band, which operates on a different polarization and runs from a different pair of antennas. You can choose which beam width ones you operate at. Just quickly, as you're familiar, to design any antenna, you've got to spot from simulation, change the simulation mechanically to realize it in real life, prototype it, see if it joins up together, and then make it, and then measure it. And somewhere around here is a iterative process, so you've got to change the stuff, go back, and see if it affects it. Once you've done it, you characterize it in simulation and real life. There are some characterizations you can only do in simulation just because of the lack of equipment. So, for example, as I said, in GPR, I'm interested in near field mode, and to come up to analyze the antenna radiation pattern in near field, the experimental techniques are quite challenging. So most people sort of try to do that in simulation. So this is one way of doing it. So you can put receivers around the antenna at arbitrary distance and see what the radiation pattern looks like. Another thing that you characterize is your time domain. So signal goes in, a noise clean signal goes into the antenna, goes through the antenna, but when it comes back, depending on what the antenna is like, this signal is going to get distorted, change in shape. So you got to sort of careful with the antenna to preserve intelligent signal. So different parameters. So you classify the signal as ringing. So after the main signal, how much your signal is going to ring, and carry on. The more ringing, more energy is wasted. And if it's the level of the aperture of the ringing is higher than the target, you're going to get mask. And also look at the aperture of the actual target that comes back. So the higher it is, So this is just a summary of just down a few pictures of the fabrication process. So yeah, so started with making the pieces separately, put them together. As you realise, when you put things together, sometimes stuff doesn't add up. So you got to improvise. You got to see how you can realise it in a different way. So yeah, you can see sort of the back of the horn. The PCB antennas inside. So there's the fabricated PCBs. The most complex part of the antenna is the wall, the fins, covered with some sort of special RAM that will absorb the signal inside. And on the left, so you put all that together, and on the right, it's the final version of it. Once you've done that, you've got to measure it, and that's the other challenge. So as I said, my antenna operates at 0.5 gigahertz, and the chamber that we have, it's not really designed to operate at that low frequency, but nevertheless, I gave it a try. And with this technique, so again, you're familiar with it, you've got two antennas pointing at each other, the source antenna and the AVT and the antenna on the test, and then you sort of scan your rotating antenna and see what the radiation pattern looks like. I had to use different antennas just because we don't have another antenna that covers the low frequencies. So we have one antenna that covers one frequency and another antenna that covers the 0.5 gigahertz antenna. And then the basic sort of fundamental gain measurements and radiation pattern. And just summary of the radiation pattern. So on the left you got the experimental, on the right you got the simulation results. What came as a surprise was the low frequency one, the radiation pattern. I wasn't really expecting to get anything like it, but it came out pretty similar to the simulation. Apart from the right-hand side, it's quite different, and I'm thinking just because that could be due to the chamber not being symmetrical. So yeah, if you've been in the chamber, next to the chamber, you have the floor is covered with RAM, and the right-hand side is covered with a wooden platform. So as the antenna scans, you have different returns coming back. So that could be it. But nevertheless, it looks pretty similar. You have other frequencies, so 3.5 gigahertz, and you have the high frequency, and that's 5 gigahertz. Which are quite a good agreement. Again, I won't go through that. So this is the return loss. Something that you look up at antennas. Something that sort of I was a bit disappointed at some of the frequency at about 4 or 5 gigahertz. The simulation shows better S1 than the fabricated one, and that comes from the fabrication error. So as you know, horns are quite dependent on the roughness of their surface. If you have cut roughness, you get a lot of signal back, so you need to make it as smooth as I can. So I'm thinking that could be one reason. But again, it shows pretty good. So generally below -10, that's what you want. Other bands and the gain measurements on the right side. Coupling. So as I said, the antenna operates at different frequency band. If you want to put different bands simultaneously, we need to make sure the coupling between each port is quite low. So here, generally the coupling is about -30 or -25, depending on which band is operating. So it's quite safe to say you can operate simultaneously without any data talking to it. So moving on to the experiment with the data collection system. On the left, in the lab, we have a soil box that you can experiment. It's gone through phases of sort of multiplication, but nevertheless, it's I'm not sure the next slide. But so this is the platform. So it's a linear platform. They can sort of move it around easily in one direction. And on the right-hand side is my radar, and I'm using the VNA as radar. So, and the reason is that, as I said, in near field GPR, everything behaves like a network, and everything's part of part of overall network. So VNA is very good at characterizing things like that. And another thing that VNA is strong at, has a good dynamic range. So I had access to two different VNAs, so portable one and another bench sort of type VNA, and both have dynamic range of about 117, 120 dBs. So you could sort of detect pretty good return signals. I sort of spent a bit of time just to characterize the parameters of the VNA, or in a sense radar. So changing sampling points, see how it affects it, changing the IF bandwidth, changing the attenuation level, averaging, see how the return signal gets affected by that. Just the three sort of parameters that I thought could influence it. The attenuation level at the front of the VNA. If we go from 0 to 10 dB, it will change the return signal. So here is the setup of the antenna with a Barrett PM2 landmine at 4 centimeters. And this is a typical profile that you get back. You can just about see, so this is the first peak is the soil, as you can sort of see it's higher than the return signal, and then followed by the return signal, so the second peak followed by the return signal. The blue one is when you have no attenuation, so 0 dB. The red one is when you have 10 dB of attenuation. And the difference is, as you can see, the developed returns and everything's higher, but when you have no attenuation, the return and the peak, the return signal from the soil and the targets are sort of coincided and broadened. So you can see here, but when you remove the attenuation, when you put 10 dB attenuation, the peak of the soil and the target are now quite distinguished. So I've been operating at that level of attenuation. The other thing you can look at is changing the IF bandwidth. Again, that's something that you look at when you characterize semiconductor devices, so how much signal you put in. And depending on your range, you need to sort of carefully choose the sampling points and dynamic range. So this is changing the IF bandwidth for the VNA from very low 5.5 kilohertz to very high 3 megahertz. Not much of a difference for my application. It changes with the depth. So for 10 centimeters that I'm interested, it doesn't really change the return signal that you get back, but the noise flow after that, you get a better noise flow, lower noise flow for IF bandwidth of small. And on the right hand side, you got the sampling points. There's a little bit of so I've noticed that there's a little bit of a phase shift or phase error, depending on what sampling points you use. So if you use a very low sampling point, your return signal tends to sort of shift in range, which comes from a phase error. So in general, the higher sampling point, the better. The sandbox, so just quickly show you the sandbox. So the sandbox is divided into 4 sections. You have 4 different materials that you can test. And at the bottom, we put some sort of copper strip. So it actually tells us where the bottom of the box is. That helps us with the depth estimation. And the box is 1 meter by 1 meter, and the actual depth of the soil is about 60 centimeters. Test mine, so this is something that me and Frederick have been looking at, trying to realize the 3D models by using some sort of recent technology for 3D printing technology. So those models have been realized with 3D printers. So you can see the BS50, PM2, and anti-vehicle landmine, as well as the simple geometrical shape of circular or flat metal. We had opportunity to go to Imperial War Museum to see whether our 3D printed landmine is actually the same as the real one. Unfortunately, we couldn't take them back, so we had to measure the models there. On the left-hand side, you get the real one, and the pink one is the 3D printed one. This is the AF scan sort of data that you get back from a quartz-rich horn, 20 centimeters above the mine. You can see the profile is pretty much the same as the real one. So the 3D printer is the same profile, which is good. But the real one has a little bit more reflectivity, so higher reflectivity than a small one. So my conclusion is if you can take that, you can definitely take that. It's very good. I wanted to take this further, so I wanted to see why you get more signals you get that. So I had a chance to measure the dielectric properties of the activator of the VS50. And it's a very dense plastic, and it has a dielectric properties of 8, which is quite high, so that's why you get higher signal. Obviously, real landmines don't come in empty, they contain explosives. We don't have access to explosives, fortunately. But you can sort of look into materials, other materials, safe materials that act like it. In radar, you're concerned with dielectric properties of material, mostly, and loss tangent. So loss tangent is how much attenuation through the material, and dielectric constant is how much reflectivity comes back. Dried peanut has a dielectric property of 3. It's very close to TNT and RDX, which is again 3. But some of the landmines have different combination of materials. So BS50 is RDX. As you know, RDX is a combination of TNT and paraffin wax. PM2 is RDX. So that's, you can see on the right side, just feel the exact same amount of explosive that you can find online. And VS50, again, it's dry peanuts, but with a mixture of paraffin, wax paraffin, to just give it a bit of a realistic sort of mixture. Again, these have been sort of tested to check that the dielectric properties is pretty the same. Just moving on to actual full GPR experiment. So as I said, the first factor is antenna height. How much do you put your antenna? It will affect it. It's not as if like if you go closer, you get more antenna. If you go higher, because you're in near field, your coupling, your impedance changes as you change the antenna. So here I'm showing that if you go very high, so 24 centimeters, the return signal, again, you get a soil and a target that comes back from a PM2 landmine buried 4 centimeters below. They're quite coincided. You can see they're next to each other. But as you go down to a distance of about 5-6 centimeters, the peaks become more distinguishable and separated. Sure, you get more returns from the soil as expected, but the return signal that comes back from the target is now clearly separated from the return signal from the soil. So I've been looking at distances of 5 centimeters above the ground, and I've concluded that that's a good distance to operate. Same with other bands. So if you change other bands, there are different radiation characteristics, so you can do the same thing. And again, that shows a distance of 2.5 centimeters, blue one, as compared to 10 centimeters, which is the red one. So you can see the peaks are quite distinguishable. Now, just moving on to actual experiment. So this is lab results. So the soil box, you swoop the antenna across. Something that you should first look at is the soil itself without any targets to see what comes back. And by accident, I actually found out how the density of the soil can affect the radar signal. So through one of the experiments, I think I discussed that with you one time. Mm-hmm. So the one experiment, I realized that there are some strange, unusual high returns from one side of the box. And I wanted to check that there's anything buried or that could affect the results. So I emptied this side of the soil from the side, turned it over, and put it back in. And then when I did the experiment again, the returns were gone. And that sort of can be concluded that as the soil sort of dampens, they get sort of hardened, and that has the effect on the radar. Same scenario, but different band. So lower frequency, different, still antenna. With high frequency, you can see a lot more features popping up. So you can see the density of the hardened particles and some sort of features. With lower band, you see more layers as you go down, which is, again, different features. So proving that different frequency can tell you a different story. And this is showing for dry sand and loamy soil. You can see loamy soil there's more attenuation in loamy soil than dry sand. This is burying a PMN2 landmine 2 centimeters, 2 to 3 centimeters below the ground. Using one band, you can just about see it right here with all other features around it. Switching to other band, the layers now have gone, but the target becomes more visible right in the middle. And you can justify that by looking at the shadow that it leaves on the bottom of the box, just underneath. So that's the bottom of the box and the shadow that it leaves underneath. Different landmines. So you got the VS50 buried right there, so a bit less more highlighted. You got the PMA2, which is coming out as a nice little blob, and the big anti-vehicle landmine using high frequency band, and you can see the different features are coming out from different edges of the landmine, and you can just about see the handle of the landmine on the right hand side, on the left hand side. And then looking at different band, different scenarios. So the anti-vehicle landmine was again tested with different band, and you can see when you go to lower band, different approximately gigahertz, you see the general hyperbella, but to activate the top of the landmine is more highlighted now, as expected from the simulation. And on the right hand side, I wanted to see what we're trying to get from a mortal shell-like landmine. So this is with nothing. This is with anti-vehicle on the left hand side, and a mortar shell just on top of the pebbles. And it was found out that using low frequency, it's better than high frequency for looking at rough terrains, pebbles, and rough textures. Something that I wanted to look at, comparing my antenna with other commercial antennas. Typical antenna they use for GPR, horns, and spirals. This antenna with spirals, you can see the target, so it's a green sort of profile. As expected, the spirals are not really favorable in frequency domain. The green, the red signature comes from a quadridge antenna. So you can see the soil and the target, and the blue one is my antenna, so it's the return and that's the target. One thing that you can notice is that my one gives 2 dB higher for the return signal. Now, you might say 2 dB is small, but in GPR I think 2 dB is more, you can squeeze from it. The other thing that you can notice is that this is a scenario for a flat metal, and I think as Federico presented a journal a couple of weeks ago, something that you get when you look at flat targets is continuous resonating peaks. So you get a main peak from the target, and then the signal induces a current in the metallic target, and you get resonation coming back from the edges, and that explains the peaks there. Comparing my antenna with the horn, with the quadridge, you can see that the quadridge, the piece that comes out after it is coincided and lowering the signal. Whereas my one, actually, you can tell the physical dimension by looking at the range from here to the distance from the main peak to the last peak. So it tells the actual physical dimension, as well as being higher. And then lastly, we had a chance to perform some experiments in a different environment. So thanks to Alessio, he sort of gave us a chance to test the results in Cranfield at one of the MOD sites. And on the left-hand side is the sample kit that we use. you can see there's a map that shows which sections of the box are covered with which particular target. And then on the right hand side is the scenario as the configuration that we had. So we had sort of a couple of tripods to hold the antenna and to perform some experiments. So here I've got the vehicle buried down, and the measurements again. So you can see on the left hand side background only, showing the layers of the soil as you go down the bottom of the box, which looking at from the time domain and calculating with the correct dialysis properties comes down to be 1.5 meters deep. And then the anti-vehicle right in the middle. Something that, again, I've noticed is that when a target is present, it disturbs the soil around it to a great distance. You can compare it to. Switching to a different polarization, different antenna, you can see now the edges of the landmines get picked up compared to background. Looking at a real mortar shell, obviously empty one, diffused, buried at 6 centimeters below, and this eventually you get quite a long linear. This is quite typical for long linear targets aligned with the same polarization as the antenna. And lastly, I want to look at the roughness of the surface. So just dig up the soil in different depth and texture, and you can see that there's the variance in the level and multiple targets. So just different targets. So real risk with the PM2 mortar shell, but not in the same direction as a polarization antenna, but perpendicular to it. Just to see how it comes back. So these are buried 2 centimeters below, and anti-vehicle is just flush on the surface. I can just about see all 5 targets present. With a pretty good resolution between the 2 targets, where you can just about distinguish the 2 targets from each other. That's it. So to conclude, I've introduced antenna that has a good GPR performance. As well as that, investigated how you can use multi-frequency imaging in GPR, and how we can enhance and the data that you get back, and how it can tell a different story from the same scenario. With all the experiments that are performed, there are a large amount of experimental data that's been done on realistic model AV and AP landmines, which could be a starting point for others to study does the signal processing or signal imaging enhancement. That's about it.